So yeah, I'll be talking about something sort of strange, different. It's this generalized open learners. So this is a parametrized model of computation, and the term sort of originates in machine learning, and it basically talks about a family of neural networks, and we're going to be talking about how they're learning. You can see here that I have agents here in gray. It's because these are basically open games, and hopefully this similarity will become clear as we go on. So what are we going to be talking about today is information flow in artificial neural networks. So how things are flowing, what data is going from where, how all these things fit together. And what's the reason? Why am I doing this? This is a concrete proxy for understanding some more general systems. And this is perhaps vague, but hopefully understanding some really tangible things we can program will help us understand some more abstract systems, game theoretic even. And how it's to take two notions really seriously. The first is parametrization, and the second is bidirectionality. So we'll explain what this means, but the idea will be to categorify them, to really put them in an abstract categorical setting where we can compose them and sort of reason about them more formally. So what does this all mean? I'm going to sort of try to explaining what supervised learning with neural networks is in one slide. So we start with some unknown function whose we know the input type, we know the output type, but we don't know what the function does. So this might be something that does some sort of recognition or generating data, or it's usually something motivated in real life. But what we do know is that we have a data set of input-output pairs. So we have a list of inputs and outputs, such that the input, when it goes inside, the output Y we get, the output Y is what we get. And the goal is to find out what that function is from the data. Now, the way I'm going to be there's many ways to do this, but the way we're going to be talking about today is using something called neural networks. So very, very briefly, what these are, they are sort of a parametrized computation, which takes some sort of input X and then performs a series of computations called layers, and then computes some sort of output, which we call a prediction. So if the input to this neural network is, say, an image of a cat, expertly drawn here, encoded as a series of pixel values, images, or something like this, and there's many choices how to do that, then each successive layer, sort of this is the basic neural network, is computed. So this node in what's called the hidden layer is computed sort of as a weighted sum of all of these connections. And there could be many such nodes and many such layers. And we get a prediction out. And for instance, the network could say, well, there is a 90% chance I think this is a dog and just 10% that it's a cat and so on. And you'd be forgiven for thinking this is a dog. But what we also have is something called a label. So this is coming from our data set where we label this image saying, no, this is a cat. So what happens then? We have some sort of a function, which is called the loss function or error function, which computes some notion of a distance between these things. So it's going to say how far the network's guess was from the real one. And now is the part where magic happens. So how these neural networks are learning is essentially to sort of ask, well, how could have we changed the output here? How could have we changed the loss? For instance, we might want to make it smaller. So what can we change? Well, we can't really change our label, but we could change the prediction. And we are assuming our loss is a differentiable function. So then using that knowledge, we can compute the change in our prediction that we should have had to have the loss a little bit smaller. having done this, we can repeat this process, and we can ask, well, how could have we changed this y? So how could have we changed our weights, sort of our parameters of the learning, so that our output was changed in that direction? And then we can do that as well. And we do that for each successive layers in this network, of which there could be many. The idea being then that we have two notions here. First is that we have neural network weights which control the performance. Namely, as we change these weights, we change this computation. So this computation doesn't just happen, it's depending on some hidden inputs here. And the second notion is that we are propagating some changes backwards. And you might have heard the term backpropagation. So hopefully in this talk, what I'm going to tell you is how we can make all of this more formal, more precise. You might have noticed at one point I didn't draw the backward computation, but you can draw it, you can really reason about it formally. And there's lots of things we can talk about here, but I'm going to talk also about just this being one step of learning. And this is something that's iterated many times. So what I'm going to do is, as I said, define sort of parametrization, and I'm being intentionally vague again, of this computation which happens, and there is something coming from top, and bidirectionality formally, and compose them to get this, what's going to be a two category of generalized open learners. So I'm going to tell you about an abstract treatment of gradient-based learning. So I'm going to mention backpropagation and use the language of reverse derivative categories to talk about it. I'm going to talk about this loss function. And very importantly, something I should have mentioned here, once we compute these changes in parameters, once we've done all the round trip, we need a way to say how, given where we are, and given these changes, we can compute a new parameter value. So this is going to be the update rule. And hopefully this will be also simpler and pedagogical. There's going to be lots of drawing here, and maybe this is going to be clear. And this is going to work very interestingly on not just Euclidean spaces, but any reverse differential category, which also includes Boolean circuits, surprisingly. So these ways of updating parameters are called optimizers. I'm going to talk about them, but we're going to define them also, and also using this bidirectional language of lenses. And there's lots of stuff happening here. These optimizers are going to end up being two cells in these two categories. So this is a rough overview of the things that are happening. But so this is sort of the game plan, talking about all these things: parametrization, bidirectionality, putting them together, then talking about differentiation and giving some examples. So maybe before I start, is there any questions? Okay, maybe I should also open the chat. Okay. Okay, let's start. Parametrization. In all of this talk, we're going to be fixing a symmetric monoidal category C. So we can put things in parallel, in addition to putting things in sequence. And I'm going to define a category, a two category, in a very abstract way called para-C, to stand for parametrization. So objects in this category are just the objects of C, but a morphism between an object A and an object B is a tuple. And it's a choice of a parameter, of a type of parameter space, and a map F which goes from P times A to B. So A to B is actually P times A to B. And two cells in this category are going to be reparametrization. And a two cell, so if I have objects A and B, and a morphism F which goes from P times A to B, and a morphism G which goes from Q times A to B, a two cell between those is a map from Q to P in C, such that sort of I can go either way and I get the same thing. Namely, if I start with Q times A, I can reparameterize and then apply F, or I can just apply G, and I should be getting the same thing. So examples, there's just quite simple, just applying para to, for instance, set. This is going to be a category where maps aren't functions, they are parameterized functions. Applying this to smooth is going to be a category where maps aren't smooth maps, they're parameterized smooth maps. And applying this to categories such as optic, which I'm going to be talking about, is going to give us learners where maps are not optics, they are parameterized optics or parameterized lenses.
Bruno, can I just check? I mean, we've talked about this before, but your two cells are going in the opposite direction to the arrows in the category of elements. That's right, isn't it?
Yes, I think I have an
not quite the category, but it's the opposite of the category.
Yeah, I have an op here. Yes. It's
oh, I see. There's an op. Sorry.
Yeah. So it's also good to mention that maybe para smooth is isomorphic to a category called just para, and originally defined in, this is supposed to write para, originally defined in a paper backpropas functor, which has some of the original ideas, some of the ideas I sort of expanded on here. So this thing has a graphical language. So if I have a map P times A to B, usually in string diagram, people draw it as like this. But what I'm suggesting here is that we use sort of a two-dimensional notation where we draw the parameter on top. So this is going to simplify a bunch of things, because I also didn't tell you how composition works. So what I'm going to show you now, for instance, if you see two maps that are composed in the usual way, when you redraw them in this two-dimensional way, the composition becomes simpler. So you can slide these things up, and we can then sort of just put a box around them. And that's how composition works. It's sort of very intuitive and magical. Reparameterizations as well. If you remember the definition of reparameterization, sort of it's a map such that something happens. Well, instead of drawing them here, we can just draw the reparameterization on top. So if I have map P times A to B, this is F, I just have a map on top which reparameterizes. So there's lots of stuff going on here. I won't expand on sort of the details, but there's a tiling language of double categories, and para C is sort of a particular a subcategory of this double category. And it all works out nicely. So going back to neural networks, a neural network that sort of takes this as an input has some hidden layer and produces an output is going to look like this in our language. It takes an input, the weights are coming from top, it produces some intermediate computation, and then there's more weights coming in, and we have the final sort of output. So things to mention here, para is symmetric monoidal, so it interacts with all this structure nicely. If I have a map going if I have two maps, one which goes from A to B and is parameterized by P, and one which goes from C to D and is parameterized by Q, I can sort of imagine sort of boxing them together and really sort of hastily drawn, and I can draw them together as a map which goes from A tensor C parameterized by B tensor Q going to B tensor D. So that's going to allow us to put sort of learners in parallel. Now, what's very important to mention is that para is natural with respect to base change. So if I have a category C, I can form para C. But if I have a functor from C to D, which is symmetric monoidal, then that gives rise to a functor between para C and para D. So how does this work? How is this defined? Well, on objects, it's going to map object A to whatever G maps it to, and object B, whatever G maps it to. So it aligns with G on objects. So what's interesting to mention is how a morphism will get mapped to. Well, P is going to get mapped to GP, right? So we have to take a parameter space and a morphism to a parameter space and a morphism. Now, what is this morphism F prime? Well, we know it has to go from the parameter times input to the output. So it goes from here to here. And the question is, how do we define this composite? And it's quite simple. Well, we do sort of the only thing we can. So we have this F, and we can apply G to F. And we're going to get, if we do that, we're going to get G of P tensor A. It's going to be G of F. And this missing map is just the laxator of the monoidal functor. So this is going to be really relevant to backpropagation, where we're going to be changing the base category from C to lenses C. We're going to be augmenting things with a backward pass. And there's lots more structure on para. It's an endofunctor on symmetric monoidal categories. It's also a monad. It's a particular growth and deconstruction, and so on.
Can I check this works both on the category of symmetric monoidal categories and lax monoidal functors, and also the category of symmetric monoidal categories and strong monoidal functors, right?
Yes, I mean, so since a strong monoidal functor has additional data, right? This is going to work because it's.
If you start with something lax, you get something lax. But if you also start with something that's also strong, then you also preserve strong monoidalness, I think.
So I think so. I never really asked myself this question. Like, it feels like it should work, but maybe I assume nothing goes wrong if you do the math. Yeah. Any other questions? Okay. So that's the first part. The second component is bidirectionality. So many people might have heard about lenses, about optics, about dependent lenses. Half of the people here probably worked on containers. There is this isomorphic structure called poly that's recently being introduced. And here I'm going to really be focusing on optics, but in essence, I'm just trying not to make a distinction right now. So I'm going to be talking about bidirectionality and talking about optics as my canonical structure, but really I'm fine with switching to lenses. Eventually, I want to switch to dependent types, and this is all going to work. We should be able to just plug in dependent stuff. So that's something I have in mind. But right now, I'm going to be doing optics. So I'm going to explain what this all means. So what are optics? It's this kind of a category where morphisms aren't just sort of maps, they are bidirectional maps. So morphisms go between pairs of objects, so objects are pairs, and a morphism from xs to yr is something of this shape, where some computation is being done forward, and it saves some intermediate state. Well, so to comment on Jules's thing, I mean, it already works. We're gonna see. So, but I'm just talking about optics. So there's a forward map going. It saves some intermediate state called the residual. I'm just gonna scroll a bit, and that's being saved for the usage of the backward map, which usually does some sort of change propagation, and it could be many different things. There's this fancy coend formulation here. Now there's the same integral, but now that's a coend. And so whenever you see something of this shape, think of an optic. The thing is, there's going to be, so this is the optic, but I'm also going to be drawing optics in the comb form. And this is something you might have seen. So for instance, we see the data is going one way and then back, but we might sometimes want to talk about, say, joining a bunch of these combs together, namely about the flow of data which goes in one direction. And with these fancy effects, you can sort of see that combs that you might have heard so far about are sort of the same things as optics. So how does computation in combs work? We do a computation, we save some intermediate state, produce something, then wait for an input, and use this together with the state to give a new output. And just to mention, right, lenses and optics, or if your category is additional, by the way, your category has to be symmetric monoidal, but if it's additionally Cartesian, then lenses are isomorphic to optics. Namely, you see these maps get and put as they're usually drawn. So get goes from X to Y and put has this shape. Well, this is just an optic, right? When you just merge these things together. If you forget the internal structure of that map, of the big map on top, you get an optic. So what's one example that we're going to use today of optics? So in machine learning, I've mentioned this parameter update, and it's called gradient descent. So I'm going to tell you what it is and tell you how it's an optic. So gradient descent sort of talks about this case where we're doing some optimization and we have a particular parameter, and then we have some change in that parameter. For instance, we have gravity pulling us down. And then we have a map which takes this parameter and this change. Now, it's here purely syntactical denotation. And does some simple, it moves in the negative direction of the change multiplied by some alpha. And of course, this would be properly done with some sort of bundles, but now I'm doing a different approach. Now, this sort of looks like the put map of a lens, where I take some state and a change and I produce a new state. And if you were thinking this, well, you're absolutely correct, because this is a lens. By the way, so this is a lens that goes from PP and again to PP. The notation I'm here using as a tuple. By the way, I'm going to be switching between lenses and optics. I really don't care about the distinction at this point, so it might be confusing. So please feel free to ask. So when I write this tuple here, I mean that the get map is the identity. So it takes a parameter to a parameter, but the put map takes a parameter and a change and gives me a new parameter. This is going to be important, quite important later for learning. Now, gradient descent is one particular case of something that's called an optimizer in machine learning, this procedure of computing a new parameter value. The thing is, this is a lens, but you could, in other than just computing a new parameter value based on your parameters, you could have some state that you're remembering. Maybe if you're doing iterations at multiple time steps, maybe you could collect some history about, oh, well, I was moving this and that way, so I want to gain momentum. If I kept moving this way and now I'm suddenly moving that way, I don't want to just change. I want to sort of be biased to what I was doing. And that's one example is momentum, where you have a lens of this shape where the state is the type of P. And I'm not going to go into the detail about what it's doing actually, but all of these things are lenses. So that's quite interesting, and you can unpack this. There is something called Nestor of momentum, which does something non-trivial in the forward part. And there's all this stuff happening in machine learning called Adigrad and Adam and so on. So before I go to putting these two things together and talking about learners, is there any question about this?
I guess I've got a question about what lenses are. I mean, here it's P above P. Sometimes I think I've seen lenses where P is above Q, not necessarily the same as P. Is that right? I'm just not so familiar.
Yeah. So you're absolutely right. This could be in principle different. I think in all the cases maybe that I have showed, they were the same. Well, you see here, right? We have X, yeah. So they could be different, yes.
And they're still called lenses. Okay.
Yeah.
That's a bit of a controversial point.
Oh, golly.
I guess they're called bimorphic lenses or something.
I think I invented calling them lenses in the general case, and some people who do the kind of classic kind of lenses disagree. Anyway.
And how are they different from dialectica? How's this different from dialectica categories? Sorry, but maybe that's going off on a tangent.
Again, they're related. So in a dialectica category, there's extra data. You have a relation.
Oh, there's winning conditions. Yeah. Okay. Yeah.
Exactly.
Yeah.
But time goes clockwise, which is nice.
Yeah, so it goes this way. By the way, that's a really controversial thing. I think all combinations, some people draw lenses with sort of flipped around the mirror, and some people draw them flipped around this axis, and it's just a mess. But this is the right way because I'm doing this here, so
this is right. What I do.
Yes. All right, so let's move on. So I talked about optics. So I told you if you start with a symmetric monoidal category, you can form optics. And turns out optics are still going to be symmetric monoidal, which means that you can form para-optic. Now, this is going to be the main star of the day. And let's study this category because there's lots of stuff happening here. So if you remember what the objects in para of something are, they are just objects of whatever that something is. And objects in optics are pairs of objects in C. So objects in category para-optic are going to be pairs of objects in C. Now, a morphism in para-optic from XS to YR is going to be a choice of some parameter space, which is again going to be a pair of objects in C. I'm going to call them P and Q, and a map F. Now, a map F goes from P times X and Q times S to Y times R. So there's lots of stuff happening. And very importantly, this map is an optic. So if you're thinking what's going on, you're in luck because I'm going to explain. So let's understand really what all these types here are. So an optic consists of three things, right? I'm just going to briefly scroll backwards because I forgot to mention something. So an optic consists sort of the forward map. So first of all, of the hidden type here called the residual, of the forward map and of the backward map. And these are of this type. So one goes from X to MY for some M. So X to MY, where this is M, and from MR to S. So with this in mind, I'm going to go quickly back and understand what this optic really is. So let's unpack this. So this is now a morphism in optic C, which means M is a map in C, is an object in C. Now the map, usually they're called left and right, but I'm drawing them here on top and bottom, but I'm still using. So a map left is going to go from P times X to M times Y. And the map right is going to go from M times R to Q times S. So really, what's going on here? What are there's P, X, M, Y, R, all this stuff. So let's understand this. This is the standard shape of an optic, where I have the forward computation, some state, and backward computation. Now, the parametrized optic is going to be something interesting. If you remember me saying that parameters are flowing on top, well, this is exactly what's going to happen. So we're going to have P coming in here. This is going to be our parametrization of this computation that's happening. And this is going to be our map left. So it goes from P times X to M times Y. We see that here. Now the backwards map is going to take M times R, and it's going to produce not just an S, but now note, it's going to produce a Q. So the same way we had parameters flowing on top, now we have them flowing on bottom because the backwards part of optics is flipped. It's sort of mirrored completely. So that's how it works. And this is going to be how sort of our learning works. We're going to have inputs flowing forward. Parameters are going to influence sort of this computation. These are going to be weights. We're going to produce some output. Then this learner is, stuff is going to happen here. And this learner is going to receive some change. How far away it was from the input. And it's going to use that. Well, we saved some state also, which I forgot to mention. And we're going to use that state sort of where we were and this change to compute two things. First of all is sort of a change in our parameters. And the second of all, some change we're going to propagate back to other learners. So, if we had composed two learners like this change that was propagated back would be used in this learner and so on. And maybe, and right, very importantly, I'm going to sort of flip between drawing it like this and sometimes like this. Both of these serve a different purpose. So this is sort of the standard para thing, and this is sort of flipped. And very importantly, now I told you this category is not a category, but a two category. So, you know, we automatically get two parameter ports. But very interestingly, we also get the notion of a two cell. So if you remember, if I have a parameterized map F and a parameterized map G, then I have a notion of a reparametrization between them. And this is a map in the underlying category, which in this case is going to be an optic itself. So we're going to have a map R, which is an optic itself. And there might be lots of stuff happening. So I'm going to sort of try to explain what this really means, at least how I think about it. So this map,
yeah, just if the original category was a two category or a bi-category, the two cells would be a bit more complicated, wouldn't they? And you'd have to somehow take account of the two cells in the original category. Just wondering if you've thought about that.
Yes, and I just concluded that it's way too complex because I'm just basing this on the fact that the original category is a category, and that's it.
Yeah, I see. But it probably okay. Yes, it's be like the commuting triangle, but with a two cell in between.
Yeah, I mean
mediating. Yeah, okay. I see.
Yeah. So let's study these two cells. I took the map I drew before, and I drew it like this here, and now I drew it also. I'm going to show how it looks in sort of two different perspectives. So I have a map F here, which is PQ parametrized. So P, I'm writing here P prime, but it should be Q. And I'm going to think about what happens if I have a two cell. So remember, an optic is a comb. So if you remember, if I'm going to scroll back up, an optic is a comb of that particular shape here. And this is what we're going to use right now. So this shape is going to be used here because I can sort of draw a comb around the parameter ports of an optic. Equivalently, I can just reparameterize this on top. And you know, when I just forget the insides, I'm going to get still a parameterized optic drawn in one or two ways very hastily. So there's lots of stuff happening here. And maybe in the interest of time, I can also say very quickly that there is a category called learn from backpurpose functor, which is isomorphic to para-optic set. And I'm going to skip this proof for now, or theorem. And I'm going to sort of ask if there's any questions before I really go into more concrete things and talk about how we construct these learners.
Are the two cells the same?
Yeah, so that's the thing. Learn has what we think now sort of wrong two cells. Things are wrong there. If you try to construct some functors, they're not acting well in some equivalence classes. So we think this is sort of the right way to go about this. All right. So how do we construct some learners? How do we construct neural networks? An important thing to have in mind is differentiation, and this is what we're going to be talking about today. Essentially, this is what things such as TensorFlow, PyTorch, or JAX, or many other frameworks are doing behind the scenes. So very briefly, the notion of differentiation sort of changes can be axiomatized in many different ways. There's tangent categories, differential categories, and a particular framework I'm using, and they're all sort of similar. You could, if you squint, they're all the same thing. But the framework I'm using here is called reverse derivative categories. And essentially, these are something, categories that are like lenses. So they are sort of bidirectional. But let's study the sort of the formal definition, how it's actually defined. So a reverse differential category C is a category in which for every map F, sort of, which we're going to think of as the get map of our lens, we have a map R of F, which we're going to think of as the put map of a lens, which goes from A times B to A, subject to a bunch of conditions, which I'm going to mention. So the way to think about this is if this map f takes some input and produces some output, then this map is going to talk about derivatives. It's going to say, well, at a given point of our function, a change in b is going to produce some change in a. And you can actually flip this b and a and go, have them go the other way, and then you get forward their derivative categories. So some example, category of Euclidean spaces, like of Euclidean spaces in smooth maps, is a reverse differential category. Very interestingly, the category of Boolean circuits is a reverse differential category. So I'm going to give a very quick example. If I have a map f, which takes a number and squares it, then R of f is going to basically, at a particular point and a particular change, compute the derivative of f of this, which is going to be 2x, and multiplied by the change. So you can, in its essence, you can think of this sort of, you can think of this being the derivative times a change. So again, there's really lots of stuff happening, but maybe sort of things are going to click now, hopefully, because for each RDC, there is a symmetric monoidal functor from C into length C. I'm calling it here F, which takes a map F and gives you a length whose forward map is F, the get map is F, and the backwards map is RF. And it just works out really nicely. It sort of really neatly works out. And functoriality of this F ends up being the chain rule. And there's a bunch of these axioms in an RDC, which sort of tell you that this behaves as differentiation should. So again, lots of stuff happening. But by the way, I keep saying lenses in C, if C's are isomorphic to optics. Which brings me to my next theorem, which is that the action of para on the functor C to optic C results in a particular functor. So remember, para acted also on morphisms. I told you I'm going to scroll quickly up here. There's lots of stuff. If I have a base change, I'm going to have a para of that base change, and that's relevant to backprop. And we sort of are coming there right now. Oops, too much spoilers. Right, so an action of para on the functor f, which takes a map and augments it with the backward pass, results in a functor para f, which takes a parametrized map and gives you a parametrized optic. So it takes you can think of this as a parametrized smooth map, and it gives you an optic which takes this A, takes this B. So if this is map f, it's essentially going to be f here, while the backwards pass is going to be doing the changes. So it's going to take a change in B, produce a change in A together with this residual, and produce a change in P as well.
Can I just ask something? The reverse derivative is a little bit hard to understand. I mean, it's like saying you've got some direction in the output you want to go in, and it's saying, if you've got that direction in the output, then you better do this direction, follow this direction in the input. Is that the right kind of intuition? I'm just.
So that's a good question. I would say yes and no. Maybe we can talk about it. So I have to remember there's some really tricky things there, and some things don't behave as you would think so, but that's the intuition that gets you a long way, I would say. Yeah.
If I may, you're not really looking at vectors here, but covectors and reverse derivatives, and calling pullback of covectors. I don't know if this helps because it requires a little bit of differential.
Well, what's a covector?
A covector is a function over vectors. So instead of giving you a vector, it tells you for each vector how good it is, and it's evaluating the vector in the field of the vector space is on.
Okay.
Indeed, when you write that, you're writing a covector, not really a vector. And the operation on covectors goes the other way around than the usual differential. And that's how reverse derivatives arise.
Yeah. So there's definitely, this is not the end, right? When it comes to differentiation, I think there's some things to be said with respect to sort of the covector part here. And and how it pertains to machine learning. Yeah, I agree.
Yeah, intuitively, the loss is not really like a direction, like a vector, but it's an evaluation of how good each direction is, because it's telling you the cost each direction has associated with. So that's why you get reverse derivatives for losses.
Where can I read about this? Co-vectors and connections with reverse derivatives.
Oh, well, I really don't know, to be honest. Maybe there's something in the papers about tangent categories.
Aha. Okay.
But it's mainly something I worked out by myself, and someone one day mentioned it, and I realized it was the right thing.
But this does correspond to stuff in differential, like standard stuff in differential geometry, but that's probably not the easiest way to understand it.
Yeah,
Is something like the distinction between differentials and one forms or something like that?
Yeah, so forms are covectors, basically. Like sections of the covector bundles.
So I have to go back to third year maths at Cambridge. I'm afraid. Yeah, okay, yeah, one forms. Okay, fine. Okay.
Happy to discuss this if you want. Someday.
Yeah, thanks. That's said better than I would. Yeah. So, by the way, I should aim to finish at like 5 before, or exactly at 4.
We can run over a bit if you want, I think.
Okay, we might have to.
If you want to have a nice video.
Yeah, I mean, so here's an example of very, very, very simple one, just to show this. And again, this is without these covectors. It's very, very just with Euclidean spaces. So if you don't know about covectors, this should be simple. So there is say if we are in the reverse differential category smooth, and we have a map, a parametrized map from real numbers to real numbers, which is parametrized by sort of 2 parameters. So it takes parameters W0 and W1 and an input, and it does sort of what's called like a linear layer. It has a bias term, and it multiplies our input by this W1. Then we can compute RF of this, which is gonna take at a particular choice of parameters and input a change in Y, which is sort of here, just syntactically written dy, and it's gonna just do basic calculus. It's gonna compute how much I should change the first parameter, how much I should change the second parameter, and how much should I change the input. We can go through this. And again, the idea is, I have my inputs flowing in this way, my parameters here, I save some state, I get a change back, and then I compute a change in input, and I pass back the change in parameters. So what's really now interesting is that, and this is the drawback of not really using dependent things, because these are changes, these are bundles. So I really hope to do that. But so these sort of types are different. And the fact that these are changes, we still have to transform them into actual parameters. And this sort of brings us into the next and almost the next to last part. How does derivative-based supervised learning happen? And we're sort of putting all things together. I told you that gradient descent itself is a lens, and I told you that lenses are 2 cells in this category. So gradient descent is a 2-cell, and it's a map between learners. So remember, gradient descent is something like this. And I'm slightly speeding up, but feel free to ask me about this stuff later. So a gradient descent is a particular lens. So if I have this learner, and I'm going to just slightly zoom in. Again, this is our learner, which had 2 parameters as inputs and 2 parameters as outputs. Well, then these changes that were computed here in this comb are going to be used with the update map I showed. This is the update map to compute the new parameters. So, think about it this way. There's parameters coming in. I copy them. I use them in the learner, and then I save this computation for the update that happens in the second part of the comb, and I compute a new parameter value. And this thing together is itself a learner as well. So there is stuff happening with the loss function. I really should probably go quickly over this. What I mean is I shouldn't go quickly over this, but I'm going to give you the rough idea. is that if I have a learner here, which is the image of this functor f, which augments some parameterized map with derivative. So how does learning happen? I put some input data here. This is our cat, and I have some true label that is like it says, oh, this is definitely a cat and not a dog and stuff. So I compute, the learner computes an output y. It says this is my prediction. The loss here is also differentiable. It computes some distance. Now you might be asking, well, what do we do with this distance now? And what do we supply as the backward part? You might be thinking this is what happens, but actually this is not the case. So what we do is actually, we don't really use that number, but instead we sort of say, well, start with a change of 1, and then we essentially use the train rule to back propagate this information through the parameters. Now, inside this update, so remember, this update is the gradient descent I talked about. It's a lens whose forward path is the identity, and the backward path is this u. So this change in the parameters, together with the previous parameter, directions go here, are used to compute a new parameter value. So lots of stuff happening. I'm going to skip on basically to the main stuff and say maybe the main theorem that if you fix a RDC, if you fix some loss function data, which it has some conditions, but essentially this could be like mean squared loss. It could be the things you use in probability like softness cross entropy. And if you fix a parameter update, which would be gradient descent, momentum, or any of that stuff, you can define a functor from para C to para length C, which creates a learner. So very, very quickly, you start with para C. So you start with parameterized map, you add the backward pass with the para of F, which I talked about before. So this would be here, para of F. Then you get a sort of differentiable map. And I really did not mention these things here, but you do something funky with the loss function. You sort of augment the learner on both sides. And you do the same with the update map. You add it on top. And this is still a learner. And these are these. So this and this is an endofunctor. And what basically is being done here is a theorem from Backpropas functor, which is saying the same thing, has been taken and understood maybe compositionally. We have taken this functor and decomposed it into 3 functors and sort of decomposed the category para into para smooth, decomposed learning into para-optic of set, and there's all this structure that was happening there. So I'm going to skip over this and give you some examples. I'm going to save the questions on this chapter for later. So examples here are something we're actually working on now. So there's things to iron out here. But the rough idea is you have a learner, you have some inputs and outputs that some state and co-state. And these are the same co-state, state and co-state maybe in open games. And you have some reparametrization. So what are some examples? Well, learning on smooth is basically just this. You have a learner and the reparametrization is your gradient descent. And you can choose, so you can choose your you can choose your update map and you can choose your loss function. Now, there are things called generative adversarial networks where your learner is now not just sort of a thing that we don't care what it is, but it's a composition of a bunch of things. We have a generator and we have a discriminator. Your reparametrization, your update map is a parallel product of gradient descent on the discriminator and gradient ascent on the generator. And there's also stuff, there's a co-product here, there's things, there's lots of stuff happening here. But it shows sort of how you can think about these things more easily. At least for me, I feel like I only understood how these things work once I drew these diagrams. There's a thing called competitive gradient descent, which is sort of misleading. It's used for generative adversarial networks, where you say, well, if this is one learner, why are these things sort of just the product of the things? Maybe we could define a particular update that is smarter in some way. And I'm going to skip over what this means. There's a thing called autoencoders, which is an interesting sort of a learner where you take some inputs, and this is called the encoder network, which computes some compressed representation of your data. So, you can think of the dimensionality of Z being smaller, so the encoder has to compress it. Then you have a decoder which decompresses it. And you're learning how to compress and decompress data and hopefully extracting some high-level info. And here the gradient descent are both used for both of them. And again, there's lots of stuff happening, but I'm not going to mention. Mention it here. There is a paper called Reverse Derivative Ascent, which tells you how Boolean circuits is a reverse differential category and how you can do learning on Boolean circuits. It's really weird. Like circuits are, for some abstract meaning of differentiable, they are differentiable. And that's it. I mean, there's lots of stuff I want to do. And lots of stuff I've been doing. And by the way, this is being done with a lot of people at MSP and also with Geoffrey Cratwell, Paul Wilson, and Fabio Zanassi. But really a lot of people here, we've talked about this, and you can ask me or any one of them, hopefully. So what I want to do here is really add dependent types, make some distinction clearer here, because you don't see them without them. I'm also just learning them and understanding them more clearly. There's meta learning, there's automata learning. I mentioned these things are open games, but they didn't really say how. And I really want to talk about learning iteration or repeated games. There's open dynamical systems, which really, I'm conjecturing that learners are higher order dynamical systems. There's some really interesting stuff with dynamical systems and lenses happening. And lastly, I really am not explicitly talking about probability distributions here. So, God, I don't even know where I am, but yes, there is lots of stuff now. And maybe the last thing I want to leave you with is para and optic are pretty general structures. They are defined on symmetric monoidal categories. So we don't need anything else that you can put things together. Now, what else fits into this? This seems to fit some abstract notion of learning. And I'm really hoping to hear and hoping to expand this with like weird stuff we wouldn't expect. One of them is automata learning, but I'm sure there's others. Oh God, this is on time. That's great. So yeah, I'm done and thank you.